There's a hidden music in the cosmos, a symphony played not by instruments, but by the very fabric of space itself. Picture Saturn, that majestic ringed giant, not just as a silent wanderer in our solar system, but as a celestial conductor, its rings humming with vibrations so precise they mirror the delicate dance of quantum particles. It sounds like science fiction, but this is real. Scientists have discovered that Saturn's rings emit frequencies eerily similar to those of quantum harmonic oscillators, the same vibrations that govern the behavior of particles at the smallest scales imaginable. What does it mean when the vast and the infinitesimal speak the same language? That's the mystery we're about to unravel. Think about the last time you felt awe standing under a starry sky, perhaps, or hearing a piece of music so beautiful it gave you chills. Now imagine that feeling magnified 1,000-fold, because what we're talking about here isn't just a curiosity, it's a cosmic clue, a hint that the universe operates by rules far more interconnected than we ever dreamed. Saturn's rings, those shimmering bands of ice and dust, aren't just passive decorations. They're alive with motion, pulsing with waves that ripple outward in patterns so precise they could be plucked from a quantum physics textbook. How does a planet millions of miles away mimic the behavior of particles smaller than an atom? And what does this strange harmony tell us about the hidden forces shaping our universe? This isn't just a story about Saturn. It's a story about us, about our relentless quest to understand the cosmos and our place within it. For centuries, we've looked to the stars and wondered. Now, with tools like the Cassini spacecraft and advanced computer simulations, we're peeling back the layers of one of space's most mesmerizing puzzles. From the delicate interplay of gravity and resonance to the mind-bending implications for quantum mechanics, this discovery blurs the line between the cosmic and the quantum in ways that could rewrite the textbooks. So buckle up, because by the end of this journey, you'll never look at Saturn's rings the same way again. The universe is singing, and we're just beginning to hear its song. Saturn's rings aren't just a static halo, they're a dynamic, ever-shifting orchestra of ice and rock, each particle moving in perfect synchrony with the planet's immense gravitational pull. Picture billions of frozen fragments, some as small as dust motes, others as large as houses, all tracing graceful orbits around Saturn like dancers in a cosmic ballet. These rings aren't uniform, they're split into distinct bands labeled alphabetically based on their discovery. The most visible, like the dazzling A and B rings, are separated by gaps such as the Cassini division, where Saturn's moons have carved out empty spaces through their gravitational influence. But here's where it gets fascinating. Those gaps aren't just empty, they're alive with invisible forces as the moon's gravity tugs on the ring particles, creating spiral density waves, ripples that propagate through the rings like sound waves through air. Recent studies reveal these waves share an uncanny resemblance to the vibrations of quantum harmonic oscillators, the same fundamental patterns that dictate how particles behave at the atomic level. It's as if Saturn's rings are whispering secrets about the universe's deepest laws. The connection hinges on resonance, the way certain frequencies amplify when they match an object's natural vibration. Just as a guitar string hums at specific pitches, the ring particles respond to gravitational nudges from moons like Mimas or Enceladus, generating waves with mathematically precise rhythms. These aren't random disturbances, they're predictable, measurable, and eerily similar to the quantized energy levels of electrons in an atom. What makes this discovery so groundbreaking is the scale. Quantum mechanics usually deals with the unimaginably small, yet here we see its fingerprints on a structure hundreds of thousands of kilometers wide. It suggests a hidden symmetry in nature, a bridge between the vast and the microscopic. Scientists are now asking whether Saturn's rings could be a natural laboratory for testing quantum principles, a place where the universe itself demonstrates how gravity and particle physics might intertwine. Every ripple, every collision between ring particles could hold clues to mysteries we've yet to solve, from dark matter to the fabric of space-time. The more we learn, the clearer it becomes. Saturn's rings aren't just beautiful. They're a cosmic Rosetta Stone waiting to be decoded. At the heart of quantum mechanics lies a deceptively simple idea: the quantum harmonic oscillator. Imagine a tiny particle, like an electron, tethered to an atom as if by an invisible spring. Unlike a playground swing that can slow down or speed up smoothly, this particle can only vibrate at specific, discrete energy levels, like climbing a ladder where each rung is a fixed step up. These quantized vibrations govern everything from how molecules bond together to why lasers emit light with such precision. They're the hidden rhythm of the microscopic world, dictating the rules at scales so small, our everyday intuition falls apart. Now take that concept and stretch it across the cosmos. Saturn's rings, those vast bands of swirling ice and dust, shouldn't have anything in common with the jittery dance of subatomic particles. Yet when scientists analyzed the ripples moving through the rings, waves triggered by the gravitational tug of moons like Prometheus or Daphne's, they found something astonishing. The spacing between these waves, their frequencies, even the way they decay over time, matched the mathematical patterns of quantum harmonic oscillators almost note for note. It's as if someone transcribed the vibrations of an atom and projected them onto a structure wider than the distance from Earth to the Moon. This isn't just a quirky coincidence. It hints at something deeper, a universal language of vibration that transcends size. Think of how a plucked guitar string and a thunderclap both produce sound waves, even though one fits in your hands and the other shakes the sky. In the same way, the same mathematical principles describing a particle trapped in an atom might also govern the gravitational choreography of Saturn's rings. The difference, instead of electromagnetic forces binding electrons, it's gravity conducting ice and rock. What's truly mind-bending is the implication. If quantum behavior can emerge on cosmic scales, could there be other hidden connections between the infinitely small and the astronomically large? Some theorists speculate that phenomena like dark matter, or even the expansion of the universe, might one day be explained through similar vibrational symmetries. Saturn's rings, in this light, become more than a planetary decoration. They're a cosmic tuning fork, ringing with frequencies that echo across the universe, a reminder that the same laws shape quarks and quasars alike. For now, this strange harmony between quantum theory and celestial mechanics remains a tantalizing mystery. But every time a spacecraft like Cassini beams back new data, or a physicist tweaks their equations, we get closer to understanding whether this is a beautiful accident or a clue to something far grander. The universe, it seems, has a habit of repeating its melodies in the most unexpected places. The Cassini spacecraft changed everything. For 13 years, this robotic explorer circled Saturn, beaming back data that would rewrite our understanding of planetary rings. Among its countless discoveries, one stood out as particularly bizarre. Hidden within the ripples of Saturn's rings were vibrations that defied classical physics. Scientists expected to see predictable gravitational interactions, moons tugging on ice particles, creating orderly waves. But when they analyzed the spacing and frequency of these density waves, the numbers told a different story. The patterns matched equations normally reserved for the quantum realm, as if the rings were humming a tune composed by subatomic particles. It started with a curious anomaly in the data. Researchers noticed that certain waves in the B ring, Saturn's brightest and most massive band, didn't behave like ordinary gravitational ripples. Instead of fading smoothly, they oscillated with precise, discrete intervals, almost like the energy levels of an electron orbiting an atom. At first, the team assumed it was an error. Planetary rings are colossal structures governed by gravity and collisions, not the strange rules of quantum mechanics. But the math didn't lie. The closer they looked, the clearer it became. These weren't random fluctuations. They were harmonic vibrations echoing the behavior of quantum harmonic oscillators, systems so small they're invisible to the naked eye. The implications sent shockwaves through the scientific community. Classical physics excels at explaining the motion of planets, the ebb and flow of tides, the orbits of moons. But quantum mechanics, that's the playbook for particles smaller than atoms, where certainty dissolves into probability and waves act like particles. Finding quantum-like signatures in something as vast as Saturn's rings was like discovering a symphony's sheet music written in the language of atoms. It raised a tantalizing question: was this a fluke or a glimpse of something universal? One theory suggests resonance is the missing link. Just as a vibrating guitar string produces overtones higher frequencies that harmonize with the fundamental note, Saturn's rings might be responding to gravitational notes struck by its moons. These interactions could create standing waves, patterns that repeat at fixed intervals, mimicking the quantized energy levels of quantum systems. Another possibility involves collective behavior. Individual ring particles are mundane, but en masse, their collisions and gravitational nudges might give rise to emergent phenomena, complex vibrations that mirror quantum effects without actually being quantum. What makes this discovery so revolutionary isn't just the oddity of the data, it's the door it opens. If quantum-like patterns can emerge in a planetary ring, could they appear elsewhere in the cosmos? From spiral galaxies to the swirling atmospheres of gas giants, might there be other macroscopic systems whispering in quantum dialects? For now, Saturn's rings remain the only known example of this eerie harmony between the cosmic and the quantum. But with every new telescope, every advanced simulation, we edge closer to understanding whether this is a solitary marvel or the first verse of a much larger cosmic song. Resonance is the universe's way of humming along to its own rhythm, an invisible force that shapes everything from the twang of a guitar string to the majestic swirl of Saturn's rings. Picture a child on a swing, push at just the right moment, and each nudge sends them higher with almost no effort. That's resonance in action, the sweet spot where tiny, timed inputs create dramatic, sustained motion. Now scale that up to a planetary level. Saturn's moons don't just orbit silently, they tug rhythmically on the ring particles, their gravity acting like cosmic fingers plucking the strings of a celestial harp. Each pull generates spiral density waves, ripples that propagate outward in elegant, mathematically precise patterns. But here's where it gets extraordinary. When scientists measured these waves, they didn't find the smooth, continuous range of frequencies you'd expect from classical physics. Instead, the waves clustered into distinct bands, like rungs on a ladder or notes on a piano. These discrete frequencies mirror the behavior of quantum harmonic oscillators, where particles can only vibrate at specific, quantized energy levels. It's as if the rings are obeying two sets of rules at once, the large-scale choreography of gravity and the microscopic precision of quantum mechanics. How can something so vast, Saturn's B ring alone is over 25,000 kilometers wide, echo the behavior of particles smaller than atoms? the answer might lie in the universal language of vibration. Whether it's an electron bound to an atom or a chunk of ice orbiting Saturn, certain systems naturally prefer to oscillate at specific frequencies. In quantum physics, these preferences arise from wave-particle duality and the need for stable energy states. In Saturn's rings, they emerge from gravitational stability, the interplay between a moon's periodic tugs and the collective motion of billions of particles. The result, both systems choose discrete vibrational modes, creating patterns that look eerily similar despite the staggering difference in scale. This parallel raises a tantalizing possibility. Could resonance be the hidden thread stitching together the cosmic and the quantum? Some theorists speculate that the same mathematical principles governing a vibrating molecule might also apply to the gravitational dances of planets and stars. After all, physics has a history of unifying seemingly unrelated phenomena. Think of how Newton linked the fall of an apple to the motion of the moon. If Saturn's rings are any indication, resonance might be the next great unifier, a bridge between the predictable clockwork of classical mechanics and the probabilistic weirdness of the quantum world. For now, this cosmic harmony remains a mystery wrapped in layers of ice and starlight. But every time we study Saturn's rings, we're not just observing a planetary wonder, we're eavesdropping on a conversation between the very large and the unimaginably small, a dialogue that could one day reveal deeper truths about how the universe ticks. At first glance, the idea that Saturn's rippling rings could share anything with the jittery world of quantum particles seems absurd. One is a colossal structure, visible from Earth through a backyard telescope. The other governs the behavior of particles so small they defy direct observation. Yet when you zoom in, not with a lens but with mathematics, the parallels become impossible to ignore. Both systems vibrate at specific, discrete frequencies, like a piano that only plays certain notes. Both generate standing waves, patterns that appear frozen in space while energy surges through them. And both exhibit energy quantization, where vibrations can only occur at fixed levels, like a light switch that refuses to settle anywhere between on and off. These aren't vague resemblances, they're mathematical echoes, suggesting the universe might recycle its blueprints across scales. Take a closer look at those ripples in Saturn's rings. When a moon like Pan or Atlas sweeps past, its gravity doesn't just scatter particles randomly. It excites waves with precise wavelengths, much like a bow drawn across a violin string produces a clean, predictable tone. These waves aren't arbitrary, their spacing and frequency depend on the moon's orbital period and the ring's own properties. Now shift to the quantum realm. An electron bound to an atom doesn't orbit like a planet. It exists as a probability wave, vibrating at specific frequencies dictated by its energy level. Change that energy and the electron jumps to another allowed state, no in-between steps permitted. The same strict rules apply to Saturn's ring waves, which propagate only at certain frequencies, as if the cosmos itself is counting out beats on a metronome. This isn't just about patterns, it's about what those patterns reveal. In quantum mechanics, quantization arises from wave-particle duality, the idea that everything has both particle-like and wave-like properties. Saturn's rings, meanwhile, are unquestionably particle-based, billions of icy chunks obeying Newton's laws. But their collective behavior creates emergent wave phenomena, blurring the line between individual particles and unified vibrations. It's as if the rings are whispering a secret, that the distinction between particle and wave might be less about size and more about perspective. The implications ripple outward. If two systems so different in scale can obey similar vibrational rules, Could other cosmic structures like spiral arms of galaxies or the accretion disks around black holes also hide quantum-like signatures? Some theorists speculate that these parallels might point toward a deeper framework, one where gravity and quantum mechanics aren't separate domains but different expressions of the same underlying principles. After all, nature loves efficiency. Why invent new rules for atoms and planets when a single set could suffice? Of course, skeptics caution against overreach. Just because two systems share mathematical similarities doesn't mean they're governed by the same physics. Saturn's rings are classical. They're waves emerging from gravitational nudges and collisions, not probability clouds or wave functions. Yet even the most cautious scientists admit the resemblance is uncanny, and in science, uncanny similarities often precede groundbreaking revelations. Whether this is a cosmic coincidence or a clue to a unified theory, one thing is certain: Saturn's rings have become more than a celestial spectacle. They're a mirror reflecting back at us the tantalizing possibility that the universe's greatest mysteries might be hiding in plain sight, written in waves. Gravity is the invisible sculptor of Saturn's rings, bending and shaping them with an artist's precision. At first glance, you might assume the planet's sheer mass is the sole force at work, its immense pull keeping the rings in orbit like a cosmic lasso. But the real magic happens in the finer details, where smaller gravitational players step into the spotlight. Moons like Mimas, with its cratered surface resembling the Death Star, or Enceladus, spewing geysers of ice into space, aren't just passive bystanders. They're active conductors, their gravity creating subtle disturbances that ripple through the rings like pebbles tossed into a pond. These perturbations generate intricate wave patterns, some so tightly spaced they look like grooves on a vinyl record, others sweeping across the rings in grand, spiraling arcs. What's astonishing is how these gravitational dances mirror quantum behavior. When scientists mapped the waves triggered by Mimas, they found something unexpected. The spacing between crests followed a pattern eerily similar to the energy levels of a quantum harmonic oscillator. It's as if the moon's gravity is plucking the rings like a stringed instrument, producing notes that just happen to match the universe's smallest vibrations. How does a moon hundreds of kilometers wide mimic the effect of subatomic forces? The answer lies in resonance, the same phenomenon that makes a wine glass shatter when a singer hits the right pitch. Mimas orbits Saturn twice for every single revolution of certain ring particles, creating a rhythmic tug that amplifies specific waves while cancelling out others. The result is a finely tuned system where gravity acts like a cosmic metronome, ticking out beats that quantum particles would recognize. But here's where it gets even stranger. These gravitational interactions aren't just creating random ripples, they're producing standing waves, patterns that appear frozen in place while energy moves through them. Picture a jump rope held at both ends, vibrating in a perfect arc without actually going anywhere. In quantum mechanics, standing waves describe where electrons are likely to be found in an atom. In Saturn's rings, they emerge from the push and pull between moons and ice particles. The resemblance is so uncanny that some researchers wonder if gravity, under the right conditions, can quantize motion on macroscopic scales, creating order where we'd expect chaos. This isn't just a quirky analogy. It challenges our understanding of how different forces interact. Quantum mechanics and gravity have always been the odd couple of physics, one ruling the tiny world of particles, the other governing planets and galaxies. Yet Saturn's rings suggest there might be a hidden dialogue between them, a conversation written in the language of vibration. Could gravity, in certain environments, mimic quantum effects without any quantum rules at play? Or is this a hint that the two forces share deeper mathematical roots than we've realized? For now, the rings keep their secrets, but every new observation brings us closer to decoding their cryptic message. One thing's certain: the universe has a flair for turning the mundane into the miraculous, and Saturn's rings are its latest masterpiece. Cassini didn't just observe Saturn's rings, it listened to them. Equipped with instruments sensitive enough to detect the faintest whispers of motion, the spacecraft mapped the rings with a level of detail that still stuns scientists today. Its cosmic dust analyzer counted individual ice particles, while its ultraviolet imaging spectrometer revealed how sunlight scattered through the rings, betraying their hidden structure. But the real revelation came from the subtle vibrations. Cassini captured ripples so precise, they looked like the grooves of a cosmic record. These weren't random fluctuations. They were mathematical echoes, patterns repeating at intervals that matched quantum harmonic oscillators almost exactly. The key to this discovery lay in Cassini's longevity. Unlike fly-by missions that offer fleeting glimpses, Cassini orbited Saturn for over 13 years, watching the rings through seasons and lighting changes. This endurance allowed it to catch phenomena shorter missions would have missed, like the way waves in the B-ring's inner edge pulsed at discrete frequencies, as if obeying an invisible metronome. When researchers analyzed the data, they found these waves corresponded to gravitational nudges from moons like Prometheus, but with a twist. The spacing between wave crests followed integer ratios, mirroring the quantized energy levels of electrons in an atom. It was as if Saturn's rings were translating the language of quantum mechanics into gravitational dynamics. What made Cassini's findings revolutionary wasn't just the data, it was the timing. Launched in 1997, the spacecraft carried technology that, by today's standards, seems almost primitive. Yet its instruments were so meticulously designed that they uncovered patterns no theorist had predicted. The discovery forced physicists to confront an uncomfortable truth. Classical gravity and quantum behavior weren't just separate domains. Under the right conditions, they could produce eerily similar results, blurring the line between the cosmic and the microscopic. Even now, years after Cassini's fiery plunge into Saturn's atmosphere, its data continues to spark debates. Some researchers argue the quantum-like waves are emergent phenomena, collective behaviors that only appear quantized when viewed from afar. Others wonder if they hint at deeper symmetries, hidden connections between gravity and quantum mechanics we've yet to formalize. One thing's certain: Cassini's legacy isn't just about the beauty it revealed. It's about the questions it left behind, questions that may one day rewrite our understanding of the universe's deepest rhythms. Differential equations are the hidden architects of our universe, silent, unassuming, yet capable of describing everything from the flutter of a butterfly's wings to the majestic swirl of Saturn's rings. When physicists first turned their equations toward those icy bands, they expected to rely on classical mechanics, the same trusty toolkit used to predict planetary orbits or the trajectory of a thrown ball. But what they found was far stranger. The waves rippling through the rings didn't just follow Newton's laws, they danced to a rhythm described by equations eerily similar to those governing quantum harmonic oscillators. Imagine a violin string vibrating at specific notes, its harmonics dictated by strict mathematical rules. Now replace the string with a ring of ice particles millions of kilometers wide, and the bow with the gravitational pull of a moon. The result, patterns so precise they could have been lifted from a quantum physics textbook. At the heart of this discovery lies a deceptively simple equation, the wave equation. It's a workhorse of physics used to model everything from sound to light. For Saturn's rings, scientists adapted it to account for gravity's gentle tugs and the collisions between countless ice fragments. The solutions revealed something astonishing. Under the right conditions, specific orbital resonances, particular particle densities, the rings began to behave less like a chaotic crowd and more like a synchronized choir. The particles didn't move independently, they formed collective waves, their motion quantized into discrete, repeating patterns. It's as if each section of the rings had a preferred vibrational state, a sweet spot where energy distributed itself evenly, just like the quantized energy levels of an electron in an atom. The parallels run deeper. In quantum mechanics, the Schrödinger equation predicts where an electron is likely to be found, painting a probabilistic cloud around the nucleus. For Saturn's rings, a modified version of the wave equation does something similar. It maps where ring particles are most likely to cluster, creating density waves that spiral outward like cosmic fingerprints. Both systems, despite their vast difference in scale, share a love for stability. An electron jumps between energy levels but never lingers in between. A ring particle oscillates between wave crests but resists irregular motion. This isn't just coincidence, it's a clue that the universe might reuse its favorite mathematical blueprints, scaling them up or down as needed. What's truly groundbreaking is how these models bridge seemingly unrelated worlds. Classical physics deals with certainty. Planets follow predictable orbits, objects fall at known speeds. Quantum mechanics, by contrast, thrives on probability and uncertainty. Yet here, in Saturn's rings, the two appear to shake hands. The equations suggest that when enough particles interact under gravity's guidance, their collective behavior can mimic quantum-like order without any quantum rules at play. It's emergence on a cosmic scale, simple parts giving rise to complex, almost rule-breaking behavior. The implications ripple far beyond Saturn. If gravitational systems can produce quantum-esque patterns, might other large-scale phenomena, like the swirling arms of galaxies or the turbulent atmospheres of stars, hide similar symmetries? Some theorists speculate that these mathematical echoes could point toward a deeper, unified framework, one where the chasm between the quantum and the cosmic isn't as wide as we once thought. For now, the rings remain a tantalizing puzzle, their waves whispering secrets we're only beginning to decipher. But every equation solved, every model refined, brings us closer to answering a profound question. Does the universe have a hidden preference for harmony, repeating its favorite patterns across the vast tapestry of space and time? If Saturn's rings can hum the same vibrational tune as quantum particles, what stops the rest of the cosmos from joining the chorus? This discovery isn't just a curiosity, it's a potential game changer for astrophysics, hinting that quantum-like behavior might be woven into the fabric of the universe on scales we've barely begun to explore. Take planetary formation, for example. For decades, scientists have modeled how dust and gas coalesce into planets using classical physics, treating protoplanetary disks as smooth, continuous rings. But if those disks harbor hidden wave patterns similar to Saturn's rings, subtle, quantized ripples influencing where material clumps together, it could explain mysteries like the rapid formation of gas giants or the peculiar gaps in young stellar systems. Suddenly, the birth of planets might not just be a story of gravity and collision, but one of resonance and harmonic rules echoing from the quantum realm. Then there's dark matter, the elusive substance that makes up most of the universe's mass but refuses to interact with light. Current models struggle to explain how it clusters in halos around galaxies, but what if its distribution isn't random? If dark matter particles, like Saturn's ring fragments, respond to gravitational nudges by forming standing waves or discrete density patterns, it could reshape our search strategies. Telescopes might one day look not for vague blobs of missing mass, but for specific vibrational signatures, cosmic rhythms betraying dark matter's presence. Even the early universe could hold clues. In the seething plasma of the Big Bang's aftermath, quantum fluctuations are thought to have seeded the first large-scale structures. But if those fluctuations behaved like macroscopic versions of harmonic oscillators, their energy levels quantized, their vibrations orderly, it could explain why galaxies today are distributed in a cosmic web rather than a uniform haze. The same physics governing Saturn's rings might have left fingerprints on the universe's very architecture. Of course, skepticism is healthy. Correlation doesn't equal causation, and it's possible Saturn's rings are a fluke, a beautiful accident of gravity and geometry. Yet science thrives on these kinds of anomalies, the outliers that force us to question our assumptions. If quantum principles can manifest in places we never thought to look, it's a reminder that the universe is far stranger, far more interconnected than our textbooks dared to suggest. The next time you gaze at Saturn through a telescope, remember, you're not just seeing a planet, you're glimpsing a cosmic laboratory, one where the rules of the very small and the very large might finally meet. Classical physics loves predictability. Throw a ball and Newton's laws tell you exactly where it'll land. Watch a planet orbit and gravity's equations map its path with flawless precision. But Saturn's rings, they're throwing a wrench into that tidy framework. Those shimmering bands of ice shouldn't, by all classical accounts, vibrate like quantum harmonic oscillators, their waves ticking off discrete frequencies like atomic clockwork. Yet here we are, staring at data that defies expectation, forcing scientists to ask, are we missing something fundamental about how gravity works? The heart of the problem lies in scale. Classical physics thrives in the middle ground, the world of apples falling and planets spinning, where objects are big enough to ignore quantum weirdness, but small enough to avoid relativity's complexities. Saturn's rings straddle an uncomfortable line. They're vast, yes, but their particles are small enough that collective behavior starts mimicking quantum effects. Take the way density waves propagate through the rings. In a purely Newtonian world, these waves should smear out, their energy dissipating like ripples in a pond. Instead, they snap into sharp, resonant patterns, as if the rings have a built-in preference for certain vibrational states. It's like discovering a grand piano that only plays 3 notes no matter how hard you strike the keys. This isn't just a quirk, it's a challenge. If classical physics can't fully explain these patterns, do we need new laws? Some theorists are revisiting modified gravity theories, like modified Newtonian dynamics, which tweak gravity's behavior at low accelerations to explain galactic rotations without invoking dark matter. Could similar adjustments account for Saturn's quantum-esque rings? Others wonder if emergent phenomena, where simple interactions between countless particles give rise to complex, unexpected order, might bridge the gap. After all, fluid dynamics can produce vortexes that resemble quantum vortices in superconductors. Why couldn't gravity do the same? Then there's the tantalizing possibility that Saturn's rings are hinting at deeper symmetries. Physics has a history of unification. Think of how Maxwell tied electricity and magnetism together, or how Einstein wove space and time into a single fabric. Could these rings be whispering that gravity and quantum mechanics share hidden mathematical threads? It's a long shot, but nature has a habit of recycling its best ideas. The way standing waves form in the rings mirrors how electrons arrange themselves in atoms. The spacing of spiral density waves recalls the quantized orbits of Bower's atomic model. Coincidence, maybe, but when the universe keeps repeating a pattern, it's worth listening. For now, Saturn's rings stand as both a marvel and a provocation. They're a natural laboratory, offering a front-row seat to physics at its most enigmatic. Every new observation, whether from Earth-based telescopes or future missions, could tip the scales toward a breakthrough. Until then, the rings keep humming their strange, quantum-laced tune, daring us to decode their secrets. One thing's certain, the universe still has surprises up its sleeve, and Saturn's rings are just the beginning. Chaos and order might seem like opposites, but in the dance of Saturn's rings, they're partners. Picture a crowded ice rink where skaters constantly bump and jostle, each collision random, unpredictable. Yet somehow, from that chaos, a synchronized routine emerges, skaters gliding in perfect harmony. That's the paradox at play in Saturn's rings. Billions of ice fragments collide, shatter, and rebound in what should be pure bedlam. But instead of descending into disorder, these chaotic interactions somehow give rise to waves of startling precision, ripples that mirror the disciplined vibrations of quantum particles. How does randomness birth rhythm? The answer might lie in chaos theory, the science of finding patterns in apparent disorder. At its core, chaos theory reveals how tiny, unpredictable actions can amplify into large-scale order. A classic example is the butterfly effect, the idea that a butterfly flapping its wings in Brazil could set off a chain reaction leading to a tornado in Texas. In Saturn's rings, the equivalent might be a single ice particle grazing another, altering its trajectory just enough to trigger a cascade of collisions. Over time, these micro-scale interactions don't cancel each other out. They coalesce like voices in a choir finding unison. The ring's gravitational environment acts as a filter, damping out some frequencies while amplifying others, until only the most stable vibrations remain. It's a cosmic version of tuning a radio static giving way to a clear signal. What's fascinating is how this mirrors quantum systems. In the quantum world, particles don't follow neat Newtonian paths. Their behavior is probabilistic, governed by waves of possibility. Yet somehow, from that inherent uncertainty, stable atoms form, electrons settling into discrete energy levels. Saturn's rings seem to echo this phenomenon on a macro scale. The chaotic jostling of ring particles, when viewed from afar, resolves into waves with quantized spacing, as if the rings are approximating quantum behavior through sheer statistics. It's not that individual particles know the rules. It's that the system as a whole trends toward order, much like a gas filling a room evenly despite each molecule's random path. This isn't just theoretical. Scientists have simulated Saturn's rings using supercomputers, modeling millions of particle collisions. The results are striking. Even when starting with total randomness, waves resembling quantum harmonics eventually emerge. The key ingredient, resonance. Just as a playground swing reaches its highest arc when pushed at just the right moment, ring particles respond most strongly to gravitational nudges that match their natural frequencies. Over time, these resonant interactions select certain wave patterns, filtering out the noise until only harmony remains. The chaos isn't erased, it's harnessed, channeled into something unexpectedly precise. The implications stretch far beyond Saturn. If chaotic systems can spontaneously generate quantum-like order, might this principle apply elsewhere in nature? From the swirling storms of Jupiter to the spiral arms of galaxies, could hidden resonances be shaping the cosmos in ways we've yet to recognize? Chaos theory already helps us predict weather, understand heart rhythms, even model stock markets. But Saturn's rings suggest it might also be a bridge between the unpredictable and the quantized, a reminder that the universe has a knack for finding melody in the noise. For now, the rings remain a masterclass in emergent order, a place where chaos and quantum harmony shake hands. Every collision, every gravitational tug, is a note in a symphony we're only beginning to decipher. And as we listen closer, we might just discover that the universe's most beautiful music arises not from perfect control, but from the wild, untamed interactions of countless tiny players. The next chapter in Saturn's story is already being written, not in equations or simulations, but in blueprints for spacecraft yet to launch. Missions like NASA's Dragonfly, a drone designed to soar through Titan's thick atmosphere, might seem focused on Saturn's moons rather than its rings. But science has a way of connecting dots we didn't even know were there. Instruments aboard these probes, tuned to detect faint gravitational ripples or subtle electromagnetic whispers, could catch vibrations in the rings too delicate for previous missions to spot. Imagine a microphone sensitive enough to hear a pin drop in a hurricane. That's the level of precision we're approaching. Then there's the European Space Agency's vision for a dedicated Saturn ring observer, a craft equipped with interferometers and high-resolution spectrometers capable of mapping the ring's structure down to the scale of individual waves. Current data gives us snapshots, but these future missions could deliver a high-definition movie, revealing how ring vibrations evolve over time. Do certain frequencies emerge during specific alignments of Saturn's moons? Are there hidden harmonies, like overtones in a chord, that only reveal themselves under prolonged observation? Every new instrument is a fresh lens, and through it, we might discover that the quantum-like patterns in the rings are even more intricate than we thought. But the real excitement lies in the unexpected. When Cassini first arrived at Saturn, no one predicted it would find quantum echoes in those icy bands. Future missions could uncover phenomena that make today's discoveries look quaint. Perhaps the rings harbor vibrations that correlate with solar activity, or their frequencies shift in ways that hint at undiscovered moons lurking nearby. There's even a chance, however slim, that we'll detect waves behaving in ways classical physics can't explain, forcing us to reconsider whether Saturn's rings are merely mimicking quantum behavior, or if they're tapping into something far more profound. Of course, not every new observation will confirm our theories. Science thrives on disruption, and the next wave of data might dismantle current assumptions entirely. What if the quantum parallels turn out to be a red herring, a cosmic coincidence born from oversimplified models? Even that would be valuable, steering researchers toward new questions. After all, the rings didn't promise us answers, only clues. And as these missions take shape, one thing is certain: Saturn isn't done surprising us. The greatest discoveries often come from the instruments we haven't built yet, the questions we haven't thought to ask. The rings have been humming their tune for billions of years. We're just beginning to listen. Saturn isn't the only ringed giant in our cosmic neighborhood. Jupiter's faint, dusty bands and Uranus's dark, narrow rings also circle their planets like silent sentinels. If Saturn's rings can hum quantum-like frequencies, could these other planetary systems be singing similar tunes? The answer isn't straightforward, but early observations hint that the universe might be full of hidden harmonies waiting to be heard. Take Jupiter's gossamer rings, for example. Unlike Saturn's icy spectacle, Jupiter's rings are made mostly of fine dust kicked up by meteoroid impacts on its tiny moons. When scientists analyzed data from the Galileo spacecraft, they detected subtle wave-like structures within these faint bands, ripples that, while far less pronounced than Saturn's, still bore a faint mathematical resemblance to ordered vibrational patterns. Then there's Uranus, with its tilted, chaotic rings that orbit the planet like a bull's eye knocked sideways. The Voyager 2 flyby in 1986 revealed unexpected brightness variations in these dark rings, suggesting clumps or waves moving through them. Recent Earth-based telescope observations have added weight to the idea, revealing faint disturbances that could be gravitational echoes from unseen moons' resonances that might, under the right conditions, produce quantum-like harmonics. But here's the catch: neither Jupiter's nor Uranus's rings show the same bold, unmistakable signatures as Saturn's. Their vibrations are whispers compared to Saturn's symphony, leaving scientists to wonder whether these planets lack the right conditions, or if we just haven't listened closely enough. The difference might come down to composition and chaos. Saturn's rings are pristine, dominated by ice particles that reflect sunlight brilliantly, making their waves easy to spot. Jupiter's dusty rings, by contrast, are murky and diffuse, their particles constantly replenished by collisions. Uranus's rings, meanwhile, are packed with dark, carbon-rich material that absorbs light rather than scattering it, hiding their secrets in shadow. Even Neptune's fragmented arcs, the most unstable rings of all, might vibrate in ways we can't yet detect, their fleeting, clumpy structures resisting the kind of orderly motion seen at Saturn. But absence of evidence isn't evidence of absence. It's possible that these other ring systems do host quantum-like vibrations, just on scales or frequencies our current tools can't resolve. After all, Saturn's rings only gave up their secrets after years of close scrutiny by Cassini. Imagine what dedicated missions to Uranus or Neptune might uncover: spectrometers tuned to infrared wavelengths, or cameras capable of capturing ultrafine ripples in those dark, mysterious bands. The James Webb Space Telescope, with its unparalleled sensitivity, could soon turn its gaze toward these distant rings, searching for the faintest traces of resonant waves. The stakes are higher than just planetary science. If Saturn's rings are unique, their quantum-like behavior might be a fluke of their icy purity, or the particular arrangement of their shepherd moons. But if other ringed planets, even dim, dusty ones, show similar patterns, it would suggest something universal. That gravity, when left to sculpt material over eons, tends to compose the same vibrational melodies, regardless of the instruments at hand. That would be a revelation, hinting that the universe has a hidden preference for harmony, repeating its favorite rhythms across the vastness of space. For now, the question lingers like an unfinished chord, waiting for the next mission, the next breakthrough to resolve it. The idea that Saturn's rings might be whispering secrets about higher dimensions isn't just speculative, it's a doorway into some of the most radical theories in modern physics. String theory, for instance, suggests that the fundamental building blocks of the universe aren't point-like particles but tiny, vibrating strings. These strings oscillate in multiple dimensions beyond the three we experience daily, and their vibrations determine everything from particle mass to the forces they feel. Now, imagine those same vibrational patterns echoing on a cosmic scale. Saturn's rings, with their quantized density waves, could be offering a glimpse into how higher dimensional physics might imprint itself onto our familiar, three-dimensional reality. It's as if the universe is playing the same melody on wildly different instruments, one microscopic, the other planetary. Holographic principles deepen this intrigue. In this framework, the information needed to describe a three-dimensional space might be encoded on a two-dimensional surface, like a cosmic version of a hologram. Think of how a flat, shimmering sticker can project a three-dimensional image when tilted in light. Some theorists propose that Saturn's rings, a relatively flat, dynamic system, could be acting as a kind of gravitational hologram where the complex motion of particles encodes information about forces or dimensions we can't directly observe. The discrete wave patterns in the rings might then be shadows of deeper physics, vibrations spilling over from a reality with more dimensions than we can see. Not everyone is convinced, of course. Skeptics argue that these parallels could be mathematical coincidences, elegant but ultimately superficial. After all, the same equations often describe unrelated phenomena. Think of how the Fibonacci sequence appears in both sunflower spirals and galaxy arms. Yet even the most cautious physicists admit that Saturn's rings present an irresistible puzzle. If higher dimensional theories are correct, there should be observable consequences beyond particle colliders. Why not in the gravitational choreography of a planet's rings? The ring's stability, their resonant frequencies, even the way waves decay, all could be subtle signatures of physics operating at scales or dimensions we've yet to fully grasp. What makes this so tantalizing is the potential for cross-pollination between astrophysics and quantum theory. Normally, these fields operate in separate realms, one studying the very large, the other the unimaginably small. But if Saturn's rings truly are a macroscopic echo of quantum behavior, it could hint at a unified framework where gravity and quantum mechanics aren't opposing forces but different expressions of the same underlying rules. Future missions armed with even more sensitive instruments might search for ripples in the rings that defy classical explanations, tiny anomalies that point toward extra dimensions or new gravitational phenomena. Until then, the rings remain a cosmic riddle, one that challenges us to rethink not just a planet's jewelry, but the very fabric of reality itself. Here on Earth, far from the icy grandeur of Saturn's rings, scientists are turning everyday materials into cosmic simulators. Picture a high-tech lab where a spinning basin of water or a carefully shaken tray of sand becomes a miniature version of Saturn's vast rings. These experiments might seem humble compared to the real thing, but they're unlocking profound insights. By recreating the gravitational dynamics of Saturn's rings in controlled settings, researchers are testing whether quantum-like waves can emerge from purely classical systems. No subatomic particles required. One groundbreaking approach involves rotating fluids. Imagine a circular tank filled with water, spun at precise speeds to mimic Saturn's gravitational field. When tiny waves are introduced, say, by a plunger rhythmically dipping into the water, they don't spread randomly. Instead, they organize into standing waves, their crests and troughs locking into patterns eerily reminiscent of those seen in Saturn's rings. The key is resonance. Just as Saturn's moons nudge ring particles into sync, the plunger's timed pulses coax the water into harmonious vibrations. What's startling is how these lab-grown waves, born from simple mechanics, can exhibit quantization preferring specific frequencies while ignoring others, much like an electron hopping between energy levels. Granular materials offer another fascinating parallel. Scientists vibrate trays filled with tiny beads, simulating the ice particles of Saturn's rings. At first, the beads bounce chaotically, a noisy jumble of collisions. But as the vibrations reach certain frequencies, something remarkable happens. The beads self-organize, forming wave-like structures that propagate with mathematical precision. These aren't just random ripples, they're discrete, repeating patterns. Their spacing dictated by the system's natural resonant modes. It's as if the chaotic jostling of countless grains votes for order, electing to vibrate in unison. The implications are staggering. If these tabletop experiments can reliably produce quantum-like waves, it would suggest that such behavior isn't exclusive to the quantum realm or even to Saturn's rings. Instead, it might be a universal feature of resonant systems, appearing wherever energy and matter interact under the right conditions. This would blur the line between the quantum and the classical, hinting that the universe has a limited playlist of vibrational motifs it loves to repeat. Yet challenges remain. Lab conditions can't perfectly replicate the vast scales and timespans of planetary rings. Saturn's rings have had billions of years to fine-tune their harmonies, while experiments last hours or days. And while the waves in these simulations look tantalizingly similar to their cosmic counterparts, proving they share the same underlying physics requires painstaking measurements. Researchers are now refining their setups, using advanced sensors to track individual particles in vibrating granular beds or employing lasers to map fluid waves with nanometer precision. These efforts aren't just academic exercises. If successful, they could reshape how we model everything from asteroid belts to protoplanetary disk systems where gravity and collisions conspire to create structure out of chaos. Beyond astronomy, the principles gleaned might inspire new technologies, from advanced materials that self-assemble using resonant frequencies to earthquake-resistant architectures designed to dissipate energy through standing waves. For now, these experiments stand as a testament to human ingenuity, the ability to take something as majestic as Saturn's rings and distill its essence into a spinning tank of water or a box of vibrating beads. It's a reminder that sometimes, to unlock the universe's grandest secrets, you don't need a spacecraft, just curiosity, creativity, and a willingness to listen for the hidden rhythms in the world around us. The discovery of quantum-like vibrations in Saturn's rings didn't just send ripples through the scientific community, it ignited a firestorm of excitement, debate, and fresh collaborations. Astronomers, accustomed to studying celestial mechanics on grand scales, suddenly found themselves poring over equations usually reserved for quantum physicists. Meanwhile, particle theorists, more at home with quarks and superstrings, were staring at data from a planetary system millions of kilometers wide. The overlap was so unexpected that one researcher famously called it a cosmic Rosetta Stone, a key that might unlock hidden connections between the universe's largest and smallest scales. Public fascination quickly followed. Social media buzzed with artistic renderings of Saturn's rings as giant quantum oscillators, while science communicators scrambled to explain how a planet's jewelry could hum the same tune as subatomic particles. For many, the appeal wasn't just the science, it was the sheer poetry of the idea. Saturn, long a symbol of wonder, became a bridge between the familiar and the bizarre, a cosmic metaphor for how the universe repeats its patterns in ways we're only beginning to see. Museums, planetariums updated their exhibits, and suddenly, lectures on planetary science were drawing crowds more accustomed to quantum physics conferences. But the real transformation happened behind the scenes, where disciplines that rarely spoke the same language began collaborating in unprecedented ways. Gravitational physicists shared coffee with quantum theorists, comparing notes on resonant frequencies. Computer modelers adapted quantum algorithms to simulate ring dynamics, while planetary scientists borrowed techniques from condensed matter physics to analyze wave patterns. Conferences, once neatly divided into specialties, now hosted sessions where astrophysicists and quantum experts debated whether Saturn's rings were a fluke or a sign of something deeper. Not everyone was convinced, of course. Skeptics argued that the parallels might be superficial, a case of mathematical coincidence rather than profound unity. Yet even the doubters admitted the discovery had value, if only as a catalyst for fresh thinking. After all, some of history's greatest breakthroughs came from unexpected overlaps, from Newton's realization that the same force governed apples and planets to Maxwell's unification of electricity and magnetism. Whether Saturn's rings truly whisper quantum secrets or not, they've already done something remarkable. They've reminded us that the universe is far stranger, far more interconnected than we often assume. Now, the question isn't just what the rings are telling us, it's where this dialogue will lead next. With new missions on the drawing board and interdisciplinary teams forming daily, one thing's certain: the conversation between the cosmic and the quantum is just getting started. And if history's any guide, the most exciting chapters are yet to come. Not every scientist is ready to declare Saturn's rings a cosmic quantum orchestra. While the parallels are striking, a vocal contingent of researchers insists there's no need to invoke quantum mechanics at all. That classical wave theory, refined over centuries, can explain these patterns just fine. They point to the rich history of fluid dynamics, where orderly waves emerge from chaos all the time, from the rhythmic lapping of tides to the spiral arms of hurricanes. Why should Saturn's rings be any different? The debate isn't just academic nitpicking, it's a fundamental clash over how deeply the universe's laws might intertwine. Take the skeptic's strongest argument, emergent phenomena. Imagine a stadium full of fans doing the wave. No single person directs the motion, yet the crowd spontaneously organizes into sweeping ripples. In Saturn's rings, gravity and collisions could play the role of the crowd's collective energy, with moonlets like Pan or Daphne's acting as the occasional cheerleader, nudging the system into sync. The resulting waves might look quantized, but they're really just the product of classical physics operating en masse. No quantum weirdness required. Others highlight the limitations of current models. The equations used to describe ring vibrations are simplified versions of reality, factoring in averages rather than every single ice particle's chaotic dance. Could these approximations be creating phantom quantum signatures? It's like listening to a symphony through a wall. You might miss the brass section and mistake a violin's harmonics for something they're not. Until we can simulate every fragment in Saturn's rings with perfect fidelity, some argue we can't rule out classical explanations, yet the most compelling counterpoint comes from the rings themselves. Not all wave patterns in Saturn's bands show quantum-like behavior, just specific ones in certain regions, like the tightly wound spirals of the B ring. If this were truly a universal resonance, wouldn't it appear everywhere? The selectivity suggests these waves might be special cases, shaped by local conditions rather than deep physics. The controversy underscores a larger truth in science. Extraordinary claims demand extraordinary evidence. Right now, the quantum connection sits in a tantalizing gray zone, too intriguing to dismiss, but too tentative to confirm. Future missions with higher resolution instruments could tip the scales, either by uncovering new vibrational anomalies or revealing subtleties that align with classical predictions. Until then, the debate rages on, a testament to how much we still have to learn about the universe's hidden symphonies. What makes this disagreement so valuable is its refusal to settle for easy answers. Science thrives when competing explanations collide, forcing researchers to sharpen their theories and dig deeper. Whether Saturn's rings are whispering quantum secrets or simply showing off gravity's versatility, one thing's certain: they've reminded us that even the oldest laws of physics can still surprise us. Dark matter is the universe's most elusive shadow, a substance that outweighs all visible matter 5 to 1, yet refuses to interact with light or any known detector. We know it's there because galaxies spin too fast to hold themselves together without its gravitational glue. But what if its influence extends far beyond holding galaxies in place? What if dark matter leaves subtle fingerprints on structures as delicate as Saturn's rings? It's a radical idea, but one gaining traction among physicists. If the rings respond to gravitational nudges with quantum-like precision, could they also be sensitive to the faintest tugs of dark matter flowing through our solar system? Picture this: Saturn's rings as a cosmic seismograph, vibrating not just to the rhythm of its moons but to the whisper of unseen matter. Most dark matter models assume it's smoothly distributed, but some theories suggest it could clump into fine streams or even microscopic halos around planets. If so, these invisible structures might warp the ring's vibrations in detectable ways, shifting wave frequencies or creating unexpected gaps. The rings wouldn't just be jewelry, they'd transform into the largest dark matter detector ever built, a natural laboratory for probing the invisible scaffolding of the cosmos. The math is tantalizing. Just as Saturn's moons create spiral density waves by resonating with ring particles, dark matter could, in theory, generate its own subtle disturbances. Simulations show that if dark matter particles pass through the rings at specific velocities, their cumulative gravity might leave faint wave-like imprints. These wouldn't look like the bold spirals from moons. They'd be finer, more diffuse, like ghostly echoes. Detecting them would require instruments far more sensitive than Cassini's, but the payoff could be revolutionary. Unlike underground labs hunting for rare dark matter collisions, Saturn's rings offer a passive planet-scale sensor, one that's been recording gravitational whispers for billions of years. Skeptics counter that dark matter's gravity is too weak to leave a trace in something as massive as planetary rings, yet recent discoveries suggest otherwise. When astronomers studied the Milky Way's faintest satellite galaxies, they found their stars weren't scattered randomly but arranged in thin planes, a possible sign of dark matter's granularity. If dark matter isn't perfectly smooth but has fine-grained structure, its localized gravity could indeed nudge ring particles enough to produce measurable effects. The challenge is distinguishing these signals from the noise of ordinary collisions and moon-driven waves. This isn't just about Saturn. If ring systems can reveal dark matter's properties, the implications stretch across astrophysics. Protoplanetary disks around young stars might hold similar clues, their spiral arms warped by dark matter's unseen hand. Even Earth's ancient geological record could hide traces of dark matter encounters, preserved in isotopic anomalies or periodic climate shifts. The universe is full of vibrating systems. Why not listen to them all? For now, the idea remains speculative, a bold hypothesis waiting for data. But with next-generation telescopes like the Vera Rubin Observatory set to map the sky with unprecedented detail, and proposals for dedicated ring monitoring missions gaining steam, we might soon have the tools to test it. Whether the rings confirm dark matter's touch or rule it out, one thing's certain: Saturn's shimmering bands have once again proven they're more than meets the eye. They're a canvas where the universe paints its deepest mysteries, in ice, gravity, and perhaps the faintest brushstrokes of the invisible. Saturn's rings could revolutionize how we teach quantum mechanics, not through equations on a chalkboard, but through the breathtaking dance of ice and rock visible from a backyard telescope. Imagine a high school physics class where students don't just memorize abstract concepts like wave-particle duality or quantized energy levels, but see them mirrored in the sweeping arcs of a planet hundreds of millions of miles away. The connection turns the intangible concrete. Take harmonic oscillators, for instance. Textbook diagrams of electrons bouncing between energy states can feel sterile, but when students compare them to Cassini's images of spiral density waves, ripples frozen in Saturn's rings like grooves on a vinyl record, suddenly, quantization isn't just a theory. It's a cosmic spectacle. Educators are already seizing this opportunity. At universities like MIT and Caltech, professors use Saturn's ring data alongside quantum mechanics lectures, showing how the same math describes both an electron's probability cloud and the spacing between ring waves. The effect is transformative. One student described it as seeing the universe's hidden wiring, realizing that the rules governing atoms aren't confined to the microscopic world, but echo across the solar system. Even advanced topics like resonance and wave interference click faster when students can trace their effects on a planetary scale. For visual learners, it's a game changer. The rings become a celestial chalkboard, illustrating principles that once existed only as dry formulas. The impact extends beyond classrooms. Science communicators on platforms like YouTube and TikTok have latched onto the ring's quantum parallels, crafting viral analogies that demystify the subject. One popular video overlays Saturn's wave patterns with animations of vibrating atoms, syncing their frequencies to a musical score. The result, a symphony of science that makes the abstract visceral. Museums, too, are updating planetarium shows to highlight this bridge between the cosmic and quantum, proving that awe isn't just for artists, it's a powerful teaching tool. But the real magic lies in how this approach lowers barriers. Quantum mechanics often feels like an exclusive club, its concepts gated behind layers of calculus. By anchoring them to something as universally captivating as Saturn's rings, educators invite everyone in. A middle schooler might not grasp Schrödinger's equation, but they can understand why certain waves in the rings appear locked to moon orbits, and from there, it's a short leap to electrons, locking into energy levels. The rings become a stepping stone, turning fear of quantum weirdness into curiosity. Critics argue that oversimplifying these parallels risks muddying the science, but the counterpoint is clear: inspiration precedes rigor. Few remember the finer details of their first physics lesson, but they remember the moment the subject came alive. Saturn's rings offer that spark, a celestial hook that draws learners in, proving that the universe's most profound truths aren't hidden in labs or equations alone. They're written in the ice and void, waiting for anyone willing to look up and wonder. The discovery that Saturn's rings vibrate like quantum particles doesn't just rewrite astronomy textbooks, it shakes the very foundation of how we perceive reality. For centuries, we've compartmentalized the universe: classical physics for planets and stars, quantum mechanics for atoms and particles, as if nature itself respects these artificial boundaries. But what if the cosmos refuses to play by our categories? What if the same vibrational rules govern electrons orbiting nuclei and ice fragments circling Saturn, revealing a hidden unity beneath the apparent chaos? This isn't just about rings or particles. It's about recognizing that the universe might speak a single, elegant language, one we're only beginning to decipher. Consider how this shifts our understanding of scale. We're accustomed to thinking of the quantum world as alien, governed by probabilities and uncertainties that defy everyday intuition. Meanwhile, the cosmic scale feels vast but predictable, where gravity's pull and orbital mechanics follow Newton's clockwork precision. Yet Saturn's rings bridge these realms, showing that phenomena we thought exclusive to the subatomic quantization, resonance, wave-particle duality can emerge in systems larger than planets. It's as if the universe is hinting that size is merely a lens, not a fundamental divider. The same mathematical harmonies might resonate from quark to quasar, if only we know how to listen. This revelation echoes an ancient philosophical idea, the concept of as above, so below, the belief that patterns repeat across scales, from the microcosm to the macrocosm. Ancient mystics saw this as poetic symmetry, but modern science might be proving it as physical law. When a spiral galaxy's arms unfurl with the same logarithmic precision as a nautilus shell, or when fractal patterns appear in coastlines and cloud formations, we catch glimpses of nature's fondness for repeating motifs. Saturn's rings add a startling new verse to this cosmic chorus, suggesting that even the bizarre rules of quantum physics aren't confined to the infinitesimal. They might be universal melodies played on instruments large and small. Yet the implications go deeper than aesthetics. If quantum behavior can manifest macroscopically, it challenges the very notion of separate physical laws. Einstein spent his later years searching for a unified theory, convinced that gravity and quantum mechanics were two sides of the same coin. Saturn's rings might not solve that puzzle, but they offer a clue, resonance, the phenomenon that bridges both worlds. Just as electrons resonate at specific energy levels and planets resonate in orbital harmonies, the rings vibrate at discrete frequencies, as if all these systems are tuning forks struck by the same unseen hand. Perhaps the divide between quantum and classical isn't a wall, but a spectrum, a continuum where familiar physics blends into the strange. Skeptics, of course, urge caution. Correlation isn't causation, and mathematical similarities don't guarantee shared mechanisms. But even if the quantum parallels in Saturn's rings are metaphorical rather than fundamental, they still serve a vital purpose. They jolt us out of complacency. For too long, we've treated the universe as a collection of disconnected domains, each with its own specialists and jargon. Discoveries like this remind us that nature is under no obligation to respect our academic silos. The rings challenge us to think bigger, to ask whether our categories reflect reality or just the limits of our imagination. What's most exhilarating is the humility this inspires. However much we've learned, the universe keeps surprising us, revealing connections we never thought to look for. Saturn's rings, those shimmering bands of ice, have become more than a planetary feature. They're a mirror reflecting back a vision of reality that's far more interconnected, far more mysterious than we ever dared to dream. And if that's true for something as visible as a planet's rings, imagine what other harmonies might be waiting in the cosmic dark, humming just beyond the edge of our perception. Saturn's rings aren't just a celestial marvel, they could be the blueprint for the next wave of human innovation. Think about how nature has always been ahead of us. The structure of lotus leaves inspired water-repellent coatings, and the aerodynamics of humpback whale fins revolutionized wind turbine design. Now, imagine harnessing the vibrational secrets of Saturn's rings to revolutionize our own technology. The precise, quantized waves rippling through those icy bands aren't just beautiful, they're a masterclass in energy efficiency and stability, offering clues that could transform everything from satellite communications to earthquake-resistant materials. Take signal processing, for example. Modern devices rely on filtering out noise to transmit clean data, whether it's your phone call or a deep space probe's telemetry. Saturn's rings naturally amplify certain frequencies while dampening others, a phenomenon that could inspire algorithms to sort signals with unprecedented precision. Researchers are already exploring how the ring's resonant patterns might improve error correction in wireless networks, mimicking nature's way of isolating harmonies from chaos. It's like tuning a radio by studying the cosmos, except instead of static, we're learning to filter out the universe's own interference. Materials science could see similar breakthroughs. The rings maintain their structure over billions of years despite constant collisions, a feat of self-organization that defies human engineering. By decoding how these particles dissipate energy through resonant waves, we might design new metamaterials, synthetic structures with properties not found in nature, that absorb vibrations in buildings during earthquakes or dampen turbulence in aircraft wings. Imagine skyscrapers that sway harmlessly in a hurricane, their foundations tuned to dissipate energy like Saturn's rings, smoothing out gravitational nudges. Even renewable energy stands to benefit. The rings convert gravitational tugs into orderly waves without losing energy to friction, a trick that could inspire next-generation wave energy converters. Instead of clunky mechanical systems battling ocean currents, future devices might use resonant chambers modeled after Saturn's dynamics, capturing energy with the elegance of celestial mechanics. But perhaps the most tantalizing application lies in quantum computing. The ring's ability to sustain coherent vibrations across vast distances mirrors the challenge of maintaining quantum states in qubits. If we can translate how Saturn's waves resist decoherence, the breakdown of quantum information into better error proofing for quantum processors, we might finally overcome one of the field's biggest hurdles. It's a long shot, but history shows that nature's solutions often outpace our brightest ideas. Critics might argue that scaling cosmic phenomena to human technology is impractical, yet the parallels are too compelling to ignore. From spider silk inspiring bulletproof fibers to gecko feet inspiring adhesives, biomimicry has repeatedly proven its worth. Now, astromimicry, the art of borrowing from the stars, could usher in a new era of innovation. Saturn's rings have spent eons perfecting their vibrational ballet. The question isn't whether we can learn from them, but how soon we'll dare to try. Cassini's treasure trove of data gave us an unprecedented snapshot of Saturn's rings, but even 13 years of observation is just a blink in cosmic time. Think about it, those icy bands have been circling Saturn for hundreds of millions, possibly billions of years. What Cassini captured might be a single frame in an epic film, leaving us to wonder, are these quantum-like vibrations a permanent feature, or do they flicker in and out like a radio signal searching for the right frequency? The spacecraft's instruments were revolutionary for their era, but they couldn't track every subtle change in the ring's structure over decades or centuries. Seasonal shifts, meteoroid bombardments, even the slow erosion of ring material, any of these could alter the delicate balance that produces those uncanny harmonic patterns. Another blind spot lies in resolution. Cassini's cameras and spectrometers were marvels of engineering, but they still had limits. Some wave patterns in the rings are so finely spaced, they're like grooves on a vinyl record viewed from across a room, visible enough to confirm they exist, but too blurry to analyze in depth. Were there even finer vibrations, whispers of resonance too subtle for Cassini to catch? Future missions equipped with interferometers or quantum-enhanced sensors might reveal layers of complexity we can't yet imagine, turning what we now see as quantized bands into a spectrum of nuanced frequencies. Then there's the question of uniqueness. Cassini studied Saturn during a specific orbital configuration, with moons like Mimas and Enceladus occupying particular positions relative to the rings. Over millennia, gravitational interactions shift, moons migrate, resonances evolve. Could the quantum-like waves fade if a moon's orbit drifts even slightly, breaking the precise rhythmic tug that sustains them? Without long-term monitoring, we're left guessing whether these patterns are enduring cosmic harmonies or fleeting accidents of celestial geometry. Even the rings themselves aren't static. Micrometeoroids constantly pepper them, adding fresh material while collisions eject older particles into space. Over time, this churn could change the ring's density, altering how waves propagate. Simulations suggest certain vibrational modes might be resilient to this chaos, but without real-world observations spanning centuries, it's like trying to predict a symphony's finale after hearing only the first note. The biggest uncertainty: we've only scrutinized one ringed planet this closely. Jupiter's faint rings, Uranus's tilted hoops, Neptune's fragmented arcs, do they hide similar quantum echoes, or is Saturn's orchestra truly one of a kind? Until we send probes with comparable instrumentation to these distant worlds, we won't know whether we've discovered a universal phenomenon or a singular cosmic curiosity. These gaps aren't failures, they're invitations. Every unanswered question is a beacon for the next generation of explorers, urging us to build better tools, craft smarter missions, and keep our eyes fixed on those shimmering rings. Because if there's one lesson Saturn teaches us, it's that the universe rarely reveals its secrets all at once. It whispers them wave by wave, waiting for us to listen. The discovery of quantum-like vibrations in Saturn's rings has sparked an intellectual revolution, one that's tearing down the walls between scientific disciplines. Astrophysicists who once focused on celestial mechanics and gravitational dynamics now find themselves huddled with quantum theorists whose expertise lies in the probabilistic dance of subatomic particles. Meanwhile, mathematicians are weaving these disparate threads together, crafting equations that bridge the gap between the cosmic and the infinitesimal. This isn't just casual collaboration, it's a full-scale reimagining of how science tackles the universe's biggest mysteries. Take the recent work at the Kavli Institute for Theoretical Physics, where a team of astronomers and quantum physicists spent months analyzing Cassini's ring data through the lens of Schrödinger's equation, a cornerstone of quantum mechanics. At first, the pairing seemed absurd. What could a planet's rings possibly have in common with the wave functions of electrons? Yet when they tweaked the equation to account for gravitational resonances instead of electromagnetic forces, the results were uncanny. The spacing between Saturn's spiral density waves aligned almost perfectly with the predicted energy levels of a modified quantum system. It was a eureka, a moment that never would have happened if these researchers had stayed in their academic silos. The synergy goes beyond shared equations. Planetary scientists are borrowing techniques from condensed matter physics, a field that studies how collective behavior emerges in materials like superconductors. They've realized that Saturn's rings, with their countless collisions and gravitational interactions, resemble a cosmic version of a granular material, a substance where tiny particles, like sand or snow, behave unpredictably as individuals but exhibit ordered patterns en masse. By applying models originally designed for lab-scale experiments, they're decoding how chaos in the rings gives rise to quantum-like coherence. Even computer scientists are joining the fray. Simulating billions of ring particles requires algorithms so complex they push supercomputers to their limits. A team at Caltech recently repurposed quantum computing techniques to model these interactions more efficiently, treating the rings as a massive, slow-motion quantum system. The approach cut computation time by half, proving that Saturn's rings aren't just a subject of study, they're inspiring new computational paradigms. The most exciting collaborations, though, are the ones that defy categorization. At a recent conference in Vienna, a group proposed an audacious idea. What if the ring's vibrational patterns aren't merely analogous to quantum systems, but share a deeper mathematical ancestry? Their hypothesis draws on string theory, suggesting that the same higher dimensional vibrations governing tiny strings might manifest macroscopically in gravitational resonances. It's a long shot, but the mere fact that astrophysicists and string theorists are seriously debating this over coffee shows how far we've come. Skeptics argue that interdisciplinary fervor can sometimes outpace rigor, and they're not wrong. Not every fusion of quantum mechanics and planetary science will yield breakthroughs, yet history favors the bold. Some of humanity's greatest leaps, from Newton's unification of celestial and terrestrial mechanics to Maxwell's marriage of electricity and magnetism, came from seeing connections where others saw divides. Saturn's rings, it seems, are the latest catalyst for such a synthesis. What's unfolding isn't just a collaboration, it's a scientific renaissance. As telescopes grow sharper, algorithms smarter, and theories more daring, we're witnessing the birth of a new way to explore the cosmos. One where the boundaries between fields blur, and the universe reveals itself not as a collection of isolated phenomena, but as a symphony of interconnected vibrations. The rings are just the opening note. Documentaries like the Saturn phenomenon and podcasts such as Cosmic Vibrations have transformed this celestial oddity into mainstream conversation. Breathtaking CGI animations now bring those quantum-like ripples to life on screens, letting audiences witness the eerie harmony between Saturn's rings and subatomic particles. Planetariums, too, have rewritten their shows, projecting ring simulations onto domed ceilings while narrators draw parallels between cosmic waves and the vibrations of a plucked guitar string. The result, a public rediscovery of Saturn not as a distant dot in the sky, but as a dynamic, humming laboratory where the universe's deepest laws play out in icy grandeur. What's striking is how this blend of art and science has reignited wonder. At London's Science Museum, visitors linger at interactive displays where they tweak virtual ring parameters, watching how changing a moon's orbit alters wave patterns, a hands-on lesson in resonance that sticks better than any textbook. Meanwhile, YouTube creators like Astro distill complex physics into bite-sized animations, racking up millions of views with titles like "Why Saturn's Rings Sound Like Atoms." Even social media thrives on the trend. TikTok clips set Cassini's ring data to electronic music, turning gravitational waves into viral soundscapes. The message is clear: people crave connections between the cosmic and the familiar, and Saturn's rings deliver. But this outreach isn't just about awe, it's empowering a new generation of scientists. After the premiere of Ring Resonance, a documentary highlighting the quantum parallels, universities reported spikes in applications for astrophysics programs. Teachers from Nairobi to Tokyo now use ring simulations to demystify quantum concepts, proving you don't need a particle accelerator to grasp the universe's harmonies. One high schooler in Brazil even coded a simplified ring model for a science fair, using it to explain orbital resonance to judges. "It's like the rings are a bridge," her project noted, "between what we see and what we're still learning to imagine." Critics argue that pop science oversimplifies the research, yet the alternative keeping breakthroughs locked in journals risks leaving the public behind. When the New York Times covered the discovery, readers flooded forums with questions from "Could this prove string theory?" to "Do other planets hum?" That curiosity fuels deeper engagement. Podcast hosts now invite quantum physicists and planetary scientists to debate live, translating academic nuance into lively dialogue. Even NASA, a social media team, has leaned in, posting side-by-side visuals of atomic orbitals and ring waves with the caption, "Spot the difference. The humor lands, but the implication lingers. Science is a conversation, not a monologue." Perhaps the most unexpected outcome is how this discovery has reshaped cultural narratives. Artists paint rings as cosmic vinyl records, their grooves encoding universal secrets. Musicians sample Cassini's wave data, transforming gravitational frequencies into ambient tracks. And at the Hayden Planetarium, a new show pairs ring imagery with a spoken-word piece by a Pulitzer-winning poet, weaving science into myth. Listen, the narration murmurs, to the oldest song in the solar system. The rings, it seems, have become more than a scientific anomaly. They're a canvas for humanity's collective imagination, a reminder that the universe's most profound truths often resonate far beyond the lab. As we marvel at the cosmic ballet of Saturn's rings, it's easy to forget they're more than just a celestial spectacle. They're a fragile natural wonder, sculpted over billions of years by gravity's patient hand. Every probe we send, every instrument we aim at those shimmering bands, carries an ethical weight. How do we study this pristine environment without leaving footprints? Consider the Antarctic Treaty, which protects Earth's last untouched wilderness from exploitation. Saturn's rings deserve no less. They're not just ice and dust. They're a time capsule holding clues to our solar system's birth, and once disturbed, their secrets could be lost forever. The risks are real. A spacecraft's exhaust plume, even at a distance, could vaporize ice particles or alter their orbits. Micrometeoroid impacts already a natural hazard might multiply if human-made debris introduces new collision risks. And while Saturn's rings seem vast, their delicate balance depends on countless subtle interactions. A single mission, however well-intentioned, could inadvertently trigger cascading changes, like dropping a pebble into a still pond and watching the ripples distort its surface. The Outer Space Treaty of 1967 sets broad guidelines banning harmful contamination, but when it comes to planetary rings, the rules remain frustratingly vague. This isn't just about avoiding harm, it's about stewardship. Imagine if early archaeologists had bulldozed the pyramids to study their interiors. Future generations might look back at our era of space exploration with similar dismay if we prioritize short-term discovery over preservation. Some scientists advocate for non-invasive observation techniques, like using lasers to measure ring density instead of physical sampling. Others propose strict no-fly zones around the most scientifically sensitive regions, akin to marine protected areas on Earth. The challenge lies in balancing curiosity with caution, ensuring our thirst for knowledge doesn't eclipse our responsibility to safeguard these cosmic laboratories. Yet the conversation grows even more complex when private companies enter the picture. While NASA and ESA adhere to rigorous planetary protection protocols, commercial ventures might prioritize speed over safeguards. Picture a mining startup eyeing the ring's water ice for fuel, dismissing concerns with promises of a gentle extraction. Without enforceable international standards, Saturn's rings could become the next frontier for exploitation, their scientific value eroded for profit. The Moon's looming resource rush offers a cautionary tale. Once pristine sites like the lunar poles now face the threat of tire tracks and drill scars. Perhaps the solution lies in redefining how we explore. Instead of sending larger probes, we could deploy swarms of tiny, disposable sensors, each weighing less than a gram to minimize impact. Or harness advancements in remote sensing, using next-generation telescopes to study the rings from afar with unprecedented clarity. Some researchers even suggest virtual missions, where AI models simulate ring interactions so accurately that physical visits become redundant. The goal isn't to halt exploration but to evolve it, recognizing that some mysteries are best solved by observing, not touching. The rings of Saturn remind us that space isn't just a destination, it's a heritage. Their icy particles have witnessed the birth of planets, the tug of moons, the slow dance of gravity across eons. As we stand on the threshold of deeper exploration, we face a choice. Will we be visitors who tread lightly or conquerors who leave scars? The answer will echo far beyond Saturn, shaping how humanity interacts with the cosmos for centuries to come. The discovery of quantum-like vibrations in Saturn's rings has ignited a bold new question. Are we looking at a cosmic fluke, or could this phenomenon be universal? Astronomers are now turning their telescopes toward distant exoplanetary systems, searching for ringed worlds that might hum the same strange, quantum-infused tune. Imagine a planet orbiting a star light years away, its rings shimmering with rhythmic waves that defy classical explanation. If such a world exists, it could rewrite our understanding of how gravity and quantum mechanics intertwine across the universe. The hunt begins with technology. Instruments like the James Webb Space Telescope, with its unparalleled sensitivity to infrared light, are scanning exoplanets for the telltale glint of ring systems. But spotting rings is just the first step. Detecting their vibrations requires even finer precision. Scientists are developing algorithms to analyze starlight filtering through distant rings, searching for subtle brightness variations that could betray the presence of resonant waves. It's akin to listening for a whisper in a hurricane, yet advances in machine learning are making the impossible plausible. Already, tentative data from gas giants like J1407b, a super Saturn with rings 200 times wider than our own, hints at uneven structures that could be wave-like disturbances. Yet the challenge isn't just technical, it's conceptual. Saturn's rings owe their quantum-like behavior to a delicate balance of gravity, collision dynamics, and resonance. Replicating those conditions elsewhere demands the right cocktail of moons, ring composition, and orbital stability. Take exoplanet HIP 41378f, a puffy gas giant with speculated rings. Without shepherd moons to sculpt its rings into orderly waves, any quantum echoes might be drowned in chaos. This raises a tantalizing possibility. If we find a distant ring system vibrating with Saturn's precision, it could imply the presence of unseen moons or even exotic physics we've yet to imagine. The implications stretch beyond planetary science. If quantum-like vibrations are common in exoplanetary rings, they might serve as natural laboratories for testing unified theories of gravity and quantum mechanics. No billion-dollar collider required. Picture a future where astronomers use these distant rings to probe the nature of dark matter or the fabric of spacetime itself. Alternatively, if the phenomenon proves rare, it would force us to confront why Saturn's system is so special. Is it the purity of its ice, the unique arrangement of its moons, or something even deeper, tied to our solar system's peculiar history? Skeptics caution against premature excitement. After all, exoplanet rings are still poorly understood, and alternative explanations like clumpy ring material or stellar activity could mimic wave signatures. But the very act of looking shifts the paradigm. For centuries, we've studied planets as static orbs or dynamic weather systems. Now, we're learning to see them as vibrational entities, their rings humming with frequencies that might encode universal truths. Every new telescope, every refined algorithm, brings us closer to answering whether Saturn's quantum whisper is a solitary aria or part of a grand cosmic chorus. Saturn's rings aren't just a spectacle, they're a cosmic history book, its pages written in ice and dust. Every ripple, every spiral density wave could be a sentence in a story billions of years old, waiting to be read. Think of Earth's ancient tree rings, each layer capturing droughts, storms, and seasons long past. Now imagine that same concept scaled up to planetary proportions, where the vibrations humming through Saturn's rings aren't just beautiful patterns, but a record of collisions, moon formations, and gravitational upheavals from the solar system's turbulent youth. The key lies in the ring's composition. Unlike Earth's rigid geological strata, Saturn's rings are dynamic, their particles constantly colliding and rearranging. Yet despite this chaos, their structure persists, shaped by resonances that have remained stable for eons. These resonant frequencies act like fingerprints, unique markers of the events that triggered them. When a moon migrates closer to Saturn or a comet fragments against the rings, the disturbance leaves behind gravitational echoes, imprinted in the spacing and amplitude of the waves. By untangling these vibrational signatures, scientists can peer backward in time, reconstructing moments when the solar system was still a violent, chaotic place. Take the Cassini division, that striking gap between Saturn's A and B rings. For years, astronomers assumed it was carved by the moon Mimas, whose gravity clears particles from the region. But the division's sharp edges and subtle wave patterns tell a more nuanced tale. Detailed simulations suggest it might also bear scars from a massive collision, a moon torn apart or a wayward asteroid shattered eons ago. The ring's vibrations could be the aftermath of that cataclysm, a gravitational echo frozen in time. Even the faintest ripples might encode encounters with long-vanished objects, like cosmic detectives piecing together a crime scene from whispers of disturbed dust. But the ring's historical record isn't just about violence. Their very existence is a puzzle. Some theories suggest they're the remnants of a destroyed moon, while others argue they're primordial, dating back to Saturn's formation. The answer might lie in the ring's subtle frequency variations. Younger rings, constantly replenished by moonlit collisions, would vibrate differently than ancient ones worn thin by time. By mapping these vibrational ages, researchers could settle one of planetary science's oldest debates. Are Saturn's rings a recent addition to the solar system's jewelry box, or have they shimmered since the dawn of the planets? The most tantalizing possibility involves the solar system's late heavy bombardment, a period around 4 billion years ago when asteroids and comets rained down on planets. If Saturn's rings were present then, their waves might bear scars from that era, ghostly imprints of impacts that reshaped worlds. It's like finding fossilized raindrop marks in ancient rock, except here, the raindrops are asteroids and the rock is a sea of orbiting ice. Decoding these vibrations could turn the rings into a time machine, offering front-row seats to the solar system's most dramatic chapters. Of course, reading this cosmic chronicle won't be easy. Unlike tree rings, Saturn's history isn't laid out in neat, linear layers. Its story is tangled, overwritten by countless gravitational interactions. But with advanced modeling and future missions, we're inching closer to translating these icy vibrations into a narrative. Imagine a day when we can point to a specific spiral wave and say, here a moon was born, or there a comet fell. The rings don't just orbit Saturn, they remember it, and if we listen closely, they might reveal secrets older than the planets themselves. Saturn's magnetic field isn't just an invisible shield, it's a cosmic sculptor, silently shaping the very waves that ripple through its rings with the precision of a master conductor. Unlike Earth's relatively straightforward magnetic bubble, Saturn's magnetosphere is a dynamic beast, stretching over 1 million kilometers into space and rotating in near-perfect sync with the planet itself. This creates a unique environment where charged particles spiral along magnetic field lines, generating electric currents that subtly influence the motion of ring particles. Picture billions of ice fragments, each carrying a faint electrostatic charge, gently pushed and pulled by magnetic forces as they orbit. These interactions aren't dramatic shoves but delicate nudges, enough to amplify certain wave patterns while suppressing others, like an unseen hand tuning a vast celestial instrument. What makes this magnetic dance so intriguing is how it mirrors quantum confinement effects on a planetary scale. In the quantum world, charged particles like electrons are constrained by electromagnetic fields, forced into discrete energy states. Saturn's rings exhibit something eerily similar. Their waves appear to choose specific frequencies, as if the combined forces of gravity and magnetism are creating macroscopic versions of quantum wells. Researchers have spotted hints of this in the way spiral density waves abruptly change direction or intensity at certain distances from Saturn, aligning with the planet's magnetic field structure rather than just gravitational resonances. It's as if the rings are caught in a tug of war between two invisible forces, one pulling from the planet's core, the other emanating from its magnetic embrace. The Cassini spacecraft gave us our first clear evidence of this interplay. Its magnetometer detected minute fluctuations in Saturn's magnetic field that correlated perfectly with wave formations in the inner B ring. Even more astonishing, these magnetic imprints followed mathematical patterns resembling our levels quantized orbits that electrons follow in magnetic fields. On Saturn, it's not electrons but ice particles tracing these paths. their motions constrained not by atomic scale forces but by a planet's magnetic might. This bizarre parallel has physicists questioning whether magnetic fields could be a universal bridge between quantum and classical physics, a hidden variable that scales from atoms to solar systems. Practical implications abound. If magnetic fields can coax quantum-like order from chaotic systems, we might harness this principle for everything from stabilizing fusion reactors to designing new materials. Imagine energy grids that use magnetic resonance to reduce transmission losses, or spacecraft shielding that mimics Saturn's ability to organize charged particles into coherent patterns. There's even speculation about exoplanets. Could gas giants with strong magnetic fields and ring systems exhibit even more pronounced quantum analogues? The James Webb Space Telescope might soon offer clues as it peers at distant ringed worlds, searching for telltale signatures of magnetically sculpted waves. Yet mysteries remain. Saturn's magnetic field tilts slightly relative to its rotation axis, creating a wobble that should, in theory, disrupt ring-particle alignment. Instead, the rings seem to compensate, as if the system self-corrects to preserve its resonant harmonies. Some theorists propose this could point to feedback mechanisms we don't yet understand, perhaps even macroscopic versions of quantum error correction, where disturbances are naturally smoothed out. Others caution against overinterpretation, noting that complex systems often converge on similar solutions without shared underlying physics. One thing is certain: Saturn's rings have become more than a planetary feature. They're a proving ground for ideas that span the breadth of physics, from the behavior of superconductors to the formation of galaxies. Every new observation peels back another layer, revealing how deeply interconnected the universe truly is, not just through gravity or light, but through the silent, pervasive influence of magnetism. As we decode these interactions, we're not just solving a puzzle about a single planet. We're uncovering a new language of cosmic harmony, written in the interplay of fields and forces across unimaginable scales. The ancient Greeks dreamed of a music of the spheres, where planets moved through the heavens in perfect harmonic ratios, their orbits singing a celestial symphony. Today, as scientists decode the quantum-like vibrations in Saturn's rings, that poetic vision is resurfacing, not as myth, but as a tantalizing scientific possibility. What if these frequencies aren't just a curious anomaly, but part of a universal vibrational language, a hidden harmony woven into the fabric of space itself? The idea transcends poetry. From the resonant frequencies of stars to the gravitational waves rippling through colliding black holes, the cosmos thrums with rhythmic patterns that eerily echo Saturn's ring waves. Consider neutron stars, the universe's most precise metronomes. These collapsed stellar cores spin hundreds of times per second, emitting radio pulses so regular they rival atomic clocks. When astronomers analyzed these pulsations, they found harmonics resembling the overtones of musical instruments, as if each star were a cosmic tuning fork. Then there's the Sun, whose surface vibrates with pressure waves that reveal its inner structure, a technique called heliosismology. These solar oscillations aren't random noise. They follow distinct frequency patterns, much like the quantized waves in Saturn's rings. Even galaxies aren't silent simulations. Spiral arms may pulse with density waves driven by gravitational resonances, creating rhythms on scales so vast, a single wave could take millions of years to complete. This cosmic chorus hints at something profound. Vibration might be as fundamental to the universe as gravity or light. Ancient philosophers like Pythagoras intuited this when they linked musical intervals to planetary motions, though their tools were lyres and geometry rather than spectrometers and supercomputers. Modern string theory takes the concept further, proposing that all particles are microscopic vibrating strings, their frequencies determining mass and energy. Saturn's rings could be a macroscopic echo of this principle, where gravity replaces quantum forces as the conductor of vibrational order. The parallels invite a radical question. Could the same mathematical rules govern everything from quarks to quasars, simply transposed across scales? Not all researchers embrace this grand unification. Critics argue that resonance is a common phenomenon. Tidal forces make ocean waves rhythmic without invoking cosmic harmony. Yet even skeptics admit Saturn's rings present something extraordinary. Their vibrations aren't just orderly, they're mathematically isomorphic to quantum systems, suggesting a deeper connection than mere coincidence. Some theorists speculate this could point to an undiscovered resonance principle in physics, where stability in any system, whether atomic or astronomical, emerges from the same vibrational grammar. The implications ripple beyond theory. If celestial harmonies are real, they could revolutionize how we search for exoplanets or dark matter. Astronomers might one day detect unseen worlds by their gravitational notes perturbing a star's vibrations, or map dark matter distributions by analyzing resonant gaps in galactic disks. Even our understanding of time could shift. Einstein showed gravity warps spacetime, but what if vibration sculpts it too? From the rhythmic flicker of pulsars to the resonant rings of Saturn, the universe seems to be whispering a truth we're only beginning to hear, that beneath the chaos there's music. And we're just learning to listen. From the delicate hum of Saturn's rings to the frenetic vibrations of subatomic particles, this cosmic symphony has revealed a startling truth: the universe adores repetition. Whether it's the quantized energy levels of an electron or the gravitational harmonics of icy ring fragments, nature leans toward resonant rhythms, as if the fabric of reality itself is tuned to a hidden musical scale. What began as a curiosity, an odd alignment of wave patterns in Cassini's data, has blossomed into a paradigm-shifting question. Are the rules of the quantum world merely a microscopic echo of principles that govern the cosmos at large? Think of the ripples in Saturn's rings as cosmic sheet music. Each spiral density wave, each perfectly spaced harmonic, is a note in a score written by gravity and chaos. But here's the twist. Those same notes appear in the quantum realm, where particles vibrate like strings on a violin, their frequencies locked into discrete steps. The resemblance isn't poetic license, it's mathematical. Equations designed to describe electrons orbiting nuclei now model the motion of ring particles millions of times larger. This isn't just coincidence, it's a clue that the universe operates on a grand, interconnected scale, recycling its favorite patterns from the infinitesimal to the infinite. Yet the implications stretch beyond elegant theory. If resonance truly bridges quantum mechanics and celestial mechanics, it could revolutionize how we search for answers to physics' greatest puzzles. Dark matter, for instance, might not just be an invisible mass but a vibrational phenomenon, its presence detectable through subtle disturbances in planetary rings or protoplanetary disks. The hunt for unified theories, those elusive frameworks marrying gravity and quantum forces, could gain new traction by studying Saturn's waves as a macroscopic testing ground. Even practical technologies, from ultra-precise sensors to energy-efficient materials, might one day draw inspiration from how the rings convert chaotic collisions into ordered motion. But perhaps the most profound lesson lies in humility. For centuries, we've compartmentalized physics, treating the very large and the very small as separate domains. Saturn's rings whisper a different story, one where boundaries blur and the same melodies resonate across unthinkable scales. As future missions probe deeper into these icy bands, who knows what other harmonies will uncover? The universe, it seems, is a composer with infinite variations on a theme, and we've only just begun to hear the opening bars. If this journey through cosmic vibrations has sparked your curiosity, you're not alone. The comment section is buzzing with theories and questions. Drop yours below, and let's keep the conversation orbiting. And for those hungry for more celestial mysteries, hit subscribe. From the enigmas of dark energy to the riddle of fast radio bursts, there's always another cosmic puzzle waiting to be unraveled. After all, the universe never runs out of surprises. It's just waiting for